Right now, at this very moment, the moon is leaving us. Not tomorrow, not next year, but right now, as you're watching this video, our only natural satellite is drifting away from Earth at a measurable, accelerating rate that scientists are only now beginning to fully understand. And what NASA has been measuring for decades tells a story that completely rewrites everything you think you know about the stability of our night sky. Subscribe before we go any further, because the data we're about to walk through will fundamentally change how you see the relationship between Earth and the moon. The mental image most people carry when they think about the moon is one of perfect, unchanging stability. The moon rises, the moon sets, it governs the tides, it's been there since ancient times, and it will be there forever, unchanged and unchanging. It's a constant in an uncertain universe, a reliable marker of the night sky that has guided human navigation and inspired art and science for as long as we've looked up. But that image of permanence is an illusion, a snapshot of a moment in cosmic time that cannot and will not last. The truth is far stranger, far more scientifically interesting, and far more consequential than most people realize. The moon has been slowly but steadily retreating from Earth throughout the entire history of our solar system. And that retreat is not slowing down. It's not even staying constant. According to NASA's official measurements, made through decades of precision laser ranging experiments, the moon is currently moving away from Earth at a rate of 3.8 centimeters per year. That's 1.5 inches. That's roughly the rate at which your fingernails grow. And when you hear that number, your first instinct might be to dismiss it as negligible, trivial, something too small to matter in any meaningful way. But that instinct would be profoundly wrong. Because when you take that number and extend it across the full span of geological time, when you consider what it means for a celestial body to move outward year after year after year for millions and then billions of years, the implications become absolutely staggering. Let's start with how NASA scientists even discovered this in the first place. Because the methodology is as remarkable as the findings themselves. On the moon's surface, left behind by Apollo astronauts more than 50 years ago, there are retroreflectors, mirrors placed on the lunar landscape specifically designed to bounce light directly back toward its source. And since 1969, astronomers at observatories including the Apache Point facility in New Mexico and the Côte d'Azur station in France have been shooting laser beams at these mirrors and timing how long it takes for that light to return to Earth. The round-trip time is about 2.5 seconds. By measuring the exact arrival time of those reflected photons with nanosecond precision, scientists can calculate the distance to the moon with an accuracy of near millimeter precision. They can tell you exactly how far away the moon is at any given moment, and they can compare those measurements year after year after year to see how that distance is changing. What those measurements have revealed is consistent, undeniable, and deeply consequential. The average Earth-Moon distance is increasing. Every single year, the gap between our world and its satellite grows by 3.8 centimeters. That's not an estimate. That's not a theoretical projection. That's a direct measurement, repeated for decades, with some of the most sophisticated instrumentation ever built by human beings. And it's been happening for a very long time. If we project this current recession rate backward through geological history, using fossil records, and analyzing the layered structures in ancient rocks and coral deposits that contain information about the length of Earth's day in different eras, we can construct a picture of where the moon was in the distant past. 70 million years ago, during the late Cretaceous period when dinosaurs still walked the Earth, the moon was significantly closer to our planet than it is now, and that closer proximity had profound consequences for everything living on Earth. A day in the late Cretaceous was not 24 hours long. It was approximately 23.5 hours. Your morning would come half an hour earlier than it does now. The length of day has been increasing by approximately 1 millisecond every century since the late 1600s. A millisecond per century might seem impossibly small, but it compounds. It accumulates. It adds up to something that completely restructures the relationship between Earth's rotation and the moon's orbit. And the reason for this change is rooted in the physics of tidal forces, in the way gravity operates between two massive celestial bodies locked in orbit around each other. Here's how it works. The moon's gravity is constantly pulling on the oceans, creating two massive tidal bulges on opposite sides of the planet. One bulge on the side of Earth facing the moon, where the moon's gravity is strongest, and another on the far side of Earth, where gravity is weakest. These bulges are fundamental. Without them, we wouldn't have tides. Without the tides, life in Earth's oceans would be completely different. But there's a crucial detail that most people miss. Those tidal bulges are not perfectly aligned with the moon's current position. Earth rotates faster than the moon orbits. A day is much shorter than a lunar month. This means the tidal bulges are slightly ahead of the moon, offset by the rotation of the planet. That offset creates something called gravitational torque. It's a twisting force. The bulge that's ahead of the moon pulls on the moon gravitationally, pulling it forward in its orbit, transferring rotational energy from Earth to the moon. Earth spins slightly faster than it otherwise would, but it's constantly losing angular momentum to the moon. The moon, in turn, gains that energy. It spirals outward. Its orbit expands. The same physics that keeps the moon in orbit is slowly, inexorably pushing it away. Think of it like this. Imagine a dancer spinning with a partner. If the dancer on the inside throws their partner outward while continuing to spin, the partner spirals away, their orbit expands, they move to a higher position. And the dancer on the inside spins slightly slower from the energy of that throw. That's the Earth and Moon. We are slowly pushing our satellite away, and we can measure the result with millimeter precision. But here's where it gets really interesting. The recession rate is not uniform across history. The rate at which the moon is currently receding is not the same rate at which it receded in the dinosaur age, and it certainly won't be the same rate in 100 million years from now. The current rate of 3.8 centimeters per year is the rate for this particular moment in geological time, when the Earth-Moon system has reached its current configuration. In the past, when the moon was closer, tidal forces were stronger and the recession rate was faster. In the future, as the moon continues to recede, tidal forces will weaken and the recession will slow down. But here's what's truly shocking about what NASA has been measuring. In recent decades, there's been evidence suggesting that the recession rate might actually be increasing again, that the moon might be leaving us faster than it did just a few thousand years ago. It's a finding that contradicts the expectations of earlier models that suggest the forces driving lunar recession are more complex and more active than scientists had previously calculated. And it's the reason why NASA and space agencies around the world are intensifying their focus on lunar science. They're not just studying the moon for historical interest or academic curiosity. They're racing to understand the mechanics of a celestial body that's in the process of fundamentally restructuring the dynamics of Earth's rotation. Here's why that matters. As the moon recedes, as its orbit expands, its gravitational pull on Earth's tides weakens slightly. But at the same time, Earth's rotation continues to slow down due to tidal friction. These two effects are not balanced. The net result is that eventually, in the very far future, Earth's rotation will slow down enough that the day becomes much longer than it is now. In 50 billion years, assuming the sun hasn't expanded and engulfed both of us, Earth's rotation will have slowed to the point where the same side of the planet always faces the moon, just as the same side of the moon always faces Earth now. We call this tidal locking. And when that happens, the dynamics of Earth's climate, the weather patterns, the distribution of heat around the planet will be completely transformed. But that's the far future. What should concern us more immediately is what's happening to something that has shaped human culture and civilization for longer than we've had written history. The eclipse. Right now, at this precise moment in cosmic time, we are living through an era when total solar eclipses are possible. The moon is positioned at exactly the right distance from Earth, that its disk in the sky matches the disk of the sun. When the moon passes directly in front of the sun, it perfectly blocks out the solar photosphere and creates one of the most spectacular phenomena in nature, a total solar eclipse. Observers in the path of totality experience darkness in the middle of the day. They see the sun's corona, the delicate outer atmosphere that's normally invisible, suddenly revealed in all its glory. Stars come out during the day, the temperature drops. The world seems to stop. Total solar eclipses are rare enough to be treasured, but common enough to be experienced at least a few times in a human lifetime if you travel to see them. This is a cosmic accident, a happy coincidence of orbital mechanics and celestial geometry that has existed for some time, but will not exist forever. As the moon continues to recede, its disk in the sky will slowly shrink. In a few 100 million years, the moon will be too far away to completely block the sun. The last total solar eclipse on Earth will occur in approximately 600 million years. After that, Earth will only ever experience partial solar eclipses or annular eclipses, where the moon is too small to completely cover the sun, and a ring of the sun's surface remains visible around the moon's silhouette. That means that all future species of Earth-dwelling creatures, all future civilizations, all future humans, if we're still here, will never experience the profound, almost spiritual phenomenon of a total solar eclipse. They will never know what it's like to stand in the moon's shadow and watch day turn to night, and then back to day again in the span of minutes. We are living through a unique era in Earth's history, and most of us don't even know it. But there's something else that NASA has been carefully measuring and monitoring that makes this situation even more urgent and more scientifically significant. The moon's recession rate appears to be accelerating. Now the long-term average recession rate has been relatively stable when you average it across millions of years. But within that long-term average, there are variations. And in recent decades, high-precision measurements from NASA's Lunar Laser Ranging Facilities have detected what appears to be a slight increase in the rate at which the moon is pulling away from us. It's a small increase. We're not talking about the moon suddenly launching into the cosmic void. But it's measurable, it's consistent, and it suggests that something about the Earth-Moon system has changed, or is changing. Scientists have several hypotheses about what might be causing this. One possibility is that the distribution of mass in Earth's crust has shifted due to processes like glacial isostatic adjustment, where the rebounding of Earth's crust following the melting of ice sheets from the last glacial period is subtly altering the gravitational field and the rotational dynamics of the planet. Another possibility involves the structure of Earth's interior, the way the core, mantle, and crust interact, and how that might be affecting the efficiency of tidal energy dissipation. The physics is complex, the variables are numerous, and the data is still being analyzed. But the point is that we're not talking about a simple static situation. We're talking about an active, dynamic process that's not fully understood and that appears to be more complicated than earlier models suggested. And that's why the moon recession story is not just a story about the distant future. It's a story about how much we don't know about the fundamental dynamics of the Earth-Moon system even now, in 2026, after decades of measurement and analysis. NASA has been very straightforward about what the laser ranging experiments are telling them. They've published it in peer-reviewed journals, they've made statements and press releases, they've been transparent about both the data and the uncertainties. But the findings have not received the public attention they deserve because they're not dramatic in the short term. The moon is not falling away from us at a rate that would frighten anyone. You will not notice any change in the moon's position in the sky in your lifetime, or in your children's lifetimes, or in the lifetimes of dozens of generations of your descendants. But that's not the point. The point is that we are witnessing a slow, inexorable process that is fundamentally altering the architecture of Earth's rotation and the long-term habitability parameters of our planet. Here's something else that NASA has documented in its data. The precise mechanics of how Earth's rotational energy is being transferred to the moon are more complex than simple models suggested. Tidal dissipation in Earth's oceans is not uniform. It's concentrated in certain regions, particularly in shallow seas, and in places where tidal flows interact with continental coastlines. The Bay of Fundy in Canada has some of the most extreme tidal ranges on Earth. The North Sea experiences massive tidal flows that dissipate enormous amounts of energy. These regions are acting as the primary engines driving the transfer of rotational momentum from Earth to the moon. If you wanted to map where on Earth the process of lunar recession is actually happening, you wouldn't be looking at the whole planet equally. You'd be looking at these specific regions where tidal energy dissipation is the most intense, and that has implications for understanding not just the moon, but also for understanding ocean dynamics, weather patterns, and even the long-term future of coastal regions. Climate scientists are now beginning to incorporate these dynamics into their models because as ocean currents change due to climate change, as water levels rise, as the distribution of water mass shifts around the planet, the efficiency of tidal energy dissipation will change. And if that changes, the rate of lunar recession could change. We could be approaching a point where human activity through climate change and the modification of Earth's oceans starts to have measurable effects on the moon's orbit. It's a strange connection, but it's real. It's been modeled and it's being studied. Now, the deeper story here is that planetary science is revealing that nothing about Earth's orbital and rotational dynamics is truly static or simple. Every aspect of the system is linked to every other aspect. Change the moon's distance and you change the strength of tidal forces. Change tidal forces and you change ocean circulation patterns. Change ocean circulation, and you change climate. Change climate, and you change where humans can live and how civilization functions. Change how civilization functions, and you change how much tidal energy gets dissipated, which changes how fast the moon recedes. It's a system of extraordinary complexity, and we're still in the process of understanding its full implications. What makes this scientifically significant right now in 2026 is that NASA has committed to more intensive lunar science missions in the coming years. The Artemis program is planning to land human crews on the moon again. Space agencies are deploying increasingly sophisticated instruments to study the lunar surface, the subsurface, the dust environment. And all of this is happening because the moon is no longer just an object of scientific interest or a destination for exploration. It's a laboratory for understanding planetary dynamics, tidal physics, and the long-term evolution of habitability on Earth. Every measurement that's taken on the lunar surface, every piece of data that's collected about the moon's precise position and the forces acting on it adds to the picture of a celestial body that is actively in the process of moving away from us, a process that has profound consequences for the future of Earth and everything that lives on it. Some people ask why NASA doesn't talk about this more. Why isn't there more public discussion about the fact that the moon is leaving us? And the answer is relatively straightforward. From a human perspective, on human timescales, on the timescale of months and years and even centuries, this change is imperceptible. It's not going to affect your life or your children's lives in any way that's observable. You're not going to go outside tomorrow and notice that the moon looks smaller or that the tides are different. It's going to take hundreds of millions of years for this process to reach the point where it starts to have dramatic consequences. And because it's not an immediate threat, because it's not something that requires emergency action or urgent intervention, it tends to get less attention than it should. But that doesn't make it less important. It makes it more important in a way, because this is a process that's been happening for billions of years, that will continue happening for billions more, and that will completely reshape the planet over timescales that are almost impossible for human minds to fully grasp. The moon will not escape. We're not going to wake up one day and find that it's gone. It will take an unimaginably long time for the moon to recede to the point where it's no longer gravitationally bound to Earth, and by that time, the sun will have already engulfed both of us. But long before that happens, the moon will have moved far enough away that the dynamics we rely on now will be completely transformed. The tides will be different. The length of the day will be radically extended. The climate will be restructured. And total solar eclipses will be nothing but a distant memory in the fossil record, and the historical texts of whatever civilization, if any, still exists on Earth at that time. What we're talking about is not the end of the world. It's the slow, irreversible evolution of the world over timescales of hundreds of millions of years. And the fact that we can now measure this process with such precision, that we can point laser beams at retroreflectors left on the moon by astronauts and time their return to calculate the distance between worlds to millimeter precision, that we can peer into our own future by looking at the physics operating on the moon right now, is one of the most remarkable achievements of science. It's an achievement that deserves more attention, more discussion, and more wonder than it typically receives. The moon is leaving us. It's been leaving us since the moment it formed. And we finally have the tools and the data to measure exactly how fast it's going and to project what that means for the long-term future of Earth. And that story, the story of how a satellite is slowly receding from its primary world and what that means for billions of years of cosmic history to come, is one of the most profound scientific narratives of our time. Let me give you a specific example of just how profound these consequences could be. Imagine you're standing on a beach 600 million years from now. The landscape would be unrecognizable. The moon in the sky would be noticeably smaller than it is now. If you looked closely at ancient texts or fossil records from our era, you would read descriptions of total solar eclipses, and you would think they were myths, exaggerations, the kind of impossible phenomena that no longer occurs because it cannot occur. The last total solar eclipse would have happened hundreds of millions of years before your time. To you, it would be as legendary and unimaginable as we might find the very early Earth to be. When the moon hung so close in the sky that it would have looked enormous, when tidal forces were so intense that coastal areas would have experienced catastrophic tidal bores dozens of meters high, moving up river systems at speeds that would be impossible today. The moon has always been receding. This is not a new process. This is not something that started recently. Scientists studying the fossil record, looking at evidence from ancient rocks and coral deposits and the tracks left by organisms in sedimentary layers, have determined that this process has been ongoing for billions of years. What is new is that we can now measure it, quantify it, and project it into the future with precision that would have been impossible just 50 years ago. The Apollo retroreflectors represent one of the most enduring scientific instruments that humanity has ever created. They're not complex, they're not powered, they don't require maintenance, they're simply mirrors, precisely oriented to bounce light directly back toward its source. But they've provided decades of data, and they continue to provide data today. And the latest measurements show that the recession rate appears to be slightly accelerating compared to what it was even 10 years ago. Now, there are still uncertainties about whether this is a real acceleration or whether it's just fluctuation within the noise of the measurement. The uncertainty margins are tight, but they exist. But the fact that we're even asking this question, that we're precision enough in our measurements to detect what might be a slight change in the recession rate, shows how far planetary science has come. We're not just tracking the moon anymore. We're tracking the moon's trajectory, the forces acting on it, the subtle variations, and how those forces might be changing over time. And every bit of that knowledge feeds into our understanding of a planetary system in flux, a system where nothing is truly constant and everything is connected to everything else. One of the consequences that scientists are particularly focused on is what happens to Earth's atmospheric circulation as the moon recedes and Earth's rotation slows. The Coriolis effect, which shapes everything from hurricane formation to ocean currents to large-scale weather patterns, depends on the rate of planetary rotation. As Earth rotates more slowly, the Coriolis effect will weaken. Weather patterns will change. The jet streams that guide storm systems across continents could shift in position or intensity. This doesn't mean weather will stop or that climate will become stable. It means the climate system we've evolved to predict and understand based on measurements of a rapidly rotating 24-hour day Earth. could shift into a configuration that we don't have good models for. That's concerning from a long-term perspective. It's something that climatologists and Earth system scientists are beginning to incorporate into their models. They're running simulations of what Earth's climate could look like with a slower rotation rate, with different tidal dynamics, with a smaller moon in the sky. Some of those simulations suggest that the redistribution of heat around the planet could be dramatic. Some suggest relatively modest changes. The uncertainty reflects the fact that we're still learning how all the pieces fit together. But the research is proceeding, and the consensus is clear. Lunar recession is not just a curiosity about orbital mechanics. It's a fundamental process that will shape the habitability of Earth over timescales of hundreds of millions of years. If human civilization, or whatever form intelligence takes in the future, is to persist on this planet for a significant fraction of Earth's remaining lifespan, we'll need to understand these dynamics deeply. We'll need to account for them in our long-term planning and our understanding of how planetary systems evolve. And that's why NASA is investing in lunar science, why space agencies around the world are sending missions to the moon, why every measurement taken on that distant surface matters. Because the moon isn't just there, it's going somewhere. It's been going somewhere for billions of years, and it will keep going somewhere for billions more. And our understanding of that journey is one of the keys to understanding the long-term future of life on Earth. Thank you for watching all the way through to the end. Drop a comment telling me what surprised you most about the moon's recession and what it means for the distant future of Earth, whether it's the 3.8 centimeter annual recession rate measured with millimeter precision across 384,000 kilometers of space, the fact that total solar eclipses will vanish in 600 million years and never return, the possibility that the recession rate might be accelerating, or the simple, quietly extraordinary fact that scientists can measure the moon's distance by bouncing lasers off mirrors left behind by Apollo astronauts nearly 60 years ago, and timing how long it takes for that light to return with nanosecond precision. The ability to perceive change happening at millimeter scales across billions of kilometers, to see the moon not as a static object, but as a body in motion, heading slowly but inexorably away from us, is a testament to human ingenuity and curiosity. It's a reminder that nothing in the cosmos is truly static, that even the moon, which has seemed permanent and unchanging throughout all of human history, is actually engaged in a slow dance with physics, constantly pulled by gravity and tidal forces into a trajectory that will eventually reshape everything about Earth. Subscribe to keep following this story as new lunar missions approach, as the Artemis program moves forward, and as our understanding of how the moon is reshaping Earth's long-term future continues to evolve with each new measurement and discovery from observatories around the world. The laser ranging facilities in New Mexico and France will keep sending their pulses of light bouncing off the Apollo retroreflectors. The data will keep coming back. The measurements will keep accumulating, and our picture of the moon's inexorable departure from Earth will keep becoming clearer and more precise. The moon is leaving us, but we finally have the tools to watch it go and understand what that means for billions of years of planetary evolution to come. I'll see you in the next one.